Here we will see how to get from the real Fourier series and this coefficient in the real, how to get the complex Fourier series. Let us watch this guy and listen to him very carefully, and he will explain to you how to get the complex function, complex Fourier series from the real one.
Two intermediate steps that are quite meaningful on their own. And the first step will be to complexify the Fourier series. So far, we have stated the Fourier series in terms of cosines and sines. And you have to admit, it's a little bit unsatisfying because there are three different kinds of terms, constant, cosine, and sine. There are three different formulas for determining the coefficients. And not only that, the coefficient in front here is 1 over 2 pi, where everywhere else it's 1 over pi. So there's just something unsatisfying about the Fourier series in this form. But if we switch to complex exponentials, all of these problems will go away. And instead of being unsatisfying, it will actually be deeply satisfying. So let's get there. Let's see what the Fourier series will look like, the formula and the coefficients, the series itself and the coefficients, if instead of dealing with trigonometric functions, we dealt with equivalent complex exponentials. Okay, so we'll use this as our starting point, and that'll give us an idea of what's possible. And then we'll rederive the equivalent formulas for the coefficient. And you might think that it can't possibly be worth it because the function, and for the course of this discussion, we'll assume that the function is the real function. So the function is real, but we're representing it in complex terms. It seems like it's not worth the effort. Well, it's very much worth the effort, and you will see, as you will see. And the fact that this function is real will simply yield very attractive symmetries, as they're called. So you'll see exactly what I'm talking about. So let me go from here to the complex version of the same thing, and let's just see what happens. So what I'm going to do first is represent the cosine as the sum of the two complex conjugate complex exponentials. If you will recall, and I put it on the midterm just so that it's fresh in your mind, cosine of an angle is e to I that power, I times that angle, plus e to the minus I that angle divided by 2. So that's what will end up in case of the cosine. In the case of sine, it's minus, and you have to divide by 1 over 2i instead of 1 over 2. So that's what I'm going to do silently. I'll plug that in here, and then we'll take a step back and look at what we've got. Here we go. Very nice. Okay, very nice. Well, I don't know if it's very nice yet. It's going to be very nice in just a moment. Right now, maybe it's less nice than it was. But here's what we're going to do now. We're going to collect the like exponentials. So I'll combine e to the I and alpha, this e to the I and alpha, with this e to the I and alpha. So let's see what we get. In parentheses, we'll have a sub n, and now you have to realize that 1 over I is minus I. You guys are with me on that? So it'll be minus I bn, because I want to write the complex numbers in the more standard form. So minus I bn. Now it's plus, right? Because of this minus, and I'm bringing I to the top, it's plus I b sub n. Now, here is what I'm going to do in place. But before I do that, I would like to remark that we started with a real expression, and we broke up the real cosines and sines into complex sums of complex conjugate pairs. And that complex conjugate pairing is still present in this expression, because this guy is a complex conjugate of this, and this is clearly a complex conjugate of this. So this whole term is complex conjugate of this. In fact, this whole summation is the complex conjugate of this entire summation, and so the result remains real. But I will take this a step further. I will kind of apparently, for the moment, break that complex conjugate pairing. Because what I really want is to have like exponentials. I want these guys to be e to plus in alpha, just like these guys, so I can put them together into a single sum. And that I can do with a simple renaming. It's not even renaming, it's re-indexing this sum. Instead of going from 1 to infinity, I'll go from -1 to minus infinity, and I will write minus n. Does that make sense? And when I write minus n, pay attention, this becomes minus n. This becomes minus n, but this becomes plus in alpha. And that's when I go from -1 to minus infinity. But by convention, I have to write it as minus infinity to -1. And now they look like two series that I can combine into one. So we're going to come up with some names. We're going to call this, of course, C sub n. And then this would be C sub minus n, I guess. Yeah, that works. C sub minus n. I don't even have to write it, because if this is C sub n, then this is, by definition, is C sub minus n. And so now you will see that I have a series from minus infinity to -1. The zeroth term is missing. And then from 1 to infinity. But of course, the zeroth term is not missing. It's still right here. I will call this, I will just rename it C0. And now I have a very homogeneous sum from minus infinity to plus infinity. And it looks like this. All right, we have C sub n here, C sub n here. So it's just C sub n. Right, and C sub 0 is in here because the 0 term is included as well. E to I and alpha, because that's common for both terms. That's it. Feast your eyes on the beauty of this expression. And the interesting question is, well, what's the formula for C sub n? And of course, you can derive it by simply plugging it in here. We know what C sub n is. It's well, it's right here. And when you plug it into, and when you plug these expressions into what C sub n is, you will discover that C sub n is given by this. Okay. So I'll mention this fact that you see the complex conjugate in here. I mean, that may be slightly unexpected, right? Kind of everything is going so smoothly, you might expect to see e to the I and alpha, but because of this minus, when you put these two together in that combination, you realize you have the complex conjugate here. And there is absolutely no coincidence. In fact, you will get used to this complex conjugate being there. It's actually very natural. It's almost like you find in life that you often do something opposite to achieve the final effect. When you take a picture, old style picture with film, you get a negative, and then you have to flip it again to get the positive image. So that this negativity as an intermediate step happens very frequently. And this is one of those real life effects. That's one perspective on it. Another perspective on it is, you would see it if you said, let's ignore these. let me just say that I'm looking for a series in these terms and following the same procedure as we did before, extracting these terms. I will try to follow an analogous procedure by multiplying both sides of f of alpha equals this. And then you would realize that for that trick to work, in other words, for all the terms to drop out, except the one that you're interested in, you would have to multiply by the complex conjugate. So they more or less, quote unquote, cancel each other. And when you do the integral, it brings out c sub n. That's another perspective. I seriously recommend doing that. And you'll realize that to extract that one coefficient, you have to multiply by the complex conjugate and not by the exponential itself. That's a second perspective. And finally, the third perspective will come when you see all of this from the point of view of linear algebra and the study of inner products. And then you will realize that when you deal with inner products and in the context of complex numbers, there is that conjugate sitting right there in the definition of the inner product. And so this expression will once again be natural from the linear algebra point of view. Okay, now let me exalt the virtues of the complex series versus the real series. The only con is that you might have to take a moment, a couple of weeks maybe, to get used to this. You might still not be 100% comfortable with complex numbers, but that comes with time. You'll get used to complex numbers, and then this will be no more, what's the right word? No more uncomfortable than the real series. So with that one caveat, there are only advantages. Advantage number one, just look at it, right? Isn't it gorgeous? You agree with me in terms of simplicity? It's absolutely breathtaking. That's number one. Number two, just the simplicity of it. Instead of having three different things and three different corresponding formulas, you have one thing and one corresponding formula for all the coefficients. That's advantage number two. Advantage number three is that even if these were more monolithic, they still involve trigonometric functions. And even though I love trigonometry, I still have to admit that trigonometric functions are more cumbersome than exponentials. The names are longer, the expressions are longer, the formulas for manipulating these functions are more cumbersome, all compared to exponentials. So these are much simpler, more compact, easier to work with functions. And the related advantage is that this, excuse me, I'll point right here. This almost looks like a power series. No, it doesn't almost like a power series. It's exactly a power series. And if you call e to the I alpha x, then this is just c sub n times x to the n. So instead of being a trigonometric series, which is kind of like a power series, but not really, this is literally a power series. Just like what you studied in Calculus 3 at Drexel, if you did. And if you imagine that all of these coefficients are 1, then you have a geometric series, geometric progression, which you can add up easily, which will come in handy, hopefully by the end of this lecture. And finally, there are situations where the function that you're expanding might be complex in the first place. Well, before you couldn't do it with just sines and cosines because those are real. Now you can. So nothing but advantages. And let me go back to number one. And undeniable beauty. Beauty of simplicity. So whenever possible, when we have a function, even if it's a real function, we will write it as a complex Fourier series. And the symmetry that we'll observe is that the positive c sub positive ends and c sub negative ends are the complex conjugates of each other. And so if you imagine zeros here, here's the positive terms and here's the negative terms, you just pair them up like this. And the complex part and the imaginary parts keep canceling and you're only left with real parts. So you don't really have to deal with the complexity of it. It's just that there's this beautiful symmetry that just releases whatever kinks there are in the real formulation. So there is, once you see this, there is no going back on complex numbers. You will never, once you see this, you will never use the real series, the real Fourier series again. Unless, of course, you're doing it on the computer, and then you might have to think about, well, there are twice as many terms, even though many of them cancel. It's still more memory, more operations. Maybe I want to be more efficient, and that's what computer codes do. So computer codes don't go to this double the complexity just for the beauty of it. Actually, my computer codes do. But if you want to write a code that's twice as fast, you wouldn't do this. But that might be the only reason. Okay, so that's it. This completes the complex Fourier series.
Now, after we listened to this guy, he was amazing, honestly. I enjoy listening to him and watching him many times. Let's back to our presentation. I will pass this one. I will get back again. This is the main point of changing from the real into complex Fourier series. This is the Euler form for e to the I theta equal to cosine plus sine plus I sine. So when you subtract them or add them, you will have cosine and sine. E to the I theta plus e to the minus I theta over 2 is the cosine. E to the I theta minus e to the minus I theta over 2i is the sine. This was the key to transfer from real Fourier series into the complex Fourier series. This is what we have seen in the video. So the main point, Fourier series in the complex form has only one coefficient, Cn. This Cn covers the three coefficients, A0 and An and Bn. So it is, as he said, it has beauty when you write it down. Instead of having three coefficients, as I said, in the real Fourier series, A0, An, and Bn, you will have only one coefficient, Cn. And you can notice that C0 is A0 over 2, and Cn is the conjugate of the C minus n. Conjugate means you change the term including I. So this is coefficient, only one coefficient in the Fourier complex series, which is Cn equal to 1 over 2 pi, integrating from minus pi to pi for your function. Instead of multiplying and cosine and sine, depends on you are looking for An or Bn, you have only one guy here you multiply by. It is at minus In x. Remember again, we did use this formula when we have the period of our function is 2 pi. This is why you don't have anything L or T over 2. So this one, we did use it when we let the period of our function is 2 pi. Let's go for this nice example. We see this one in the Fourier series, for real Fourier series. So we know this kind of wave from minus pi to 0 for x is minus 1. So you have horizontal line parallel to x-axis at y equal to minus 1. And from 0 to pi, you have horizontal line parallel to x-axis at y equal to 1. This, how to find this one? Using the complex Fourier series. Yes, this is a formula for C0, exactly like A0, 1 over 2 pi. Remember, our period here, T, is 2 pi. integrating my function from minus L to L, or minus half of my period to the positive half of my period for my function. Yes, I cannot integrate from minus pi to pi because I have stepwise function. So I have to get this step alone plus this step alone, right? Yes, this is easy integration. And you substitute by the upper bound and the lower bound. Also for the next one, from the upper bound to the lower bound. So you have C naught equal to 0. If you use this one in the real, you will have the same C naught, because we know C naught is the same as A naught. There is no difference. Let's go for Cn. This Cn including what? Including An and Bn, right? And including An when n start from 1 and Bn also start from 1. How to find Cn? As I said, 1 over your period, which is 2 pi, integrating from minus half of your period, which is minus pi, into the positive half of your period. Your function, again, you are in the complex, so you have only one coefficient Cn, and you don't have cosine and sine. You have only one guy here. It is a minus in by in x. Remember, you don't have pi here because your period is 2 pi. The integration of this one is easy because this is my function. How to integrate the exponential function? You will have the same exponential function divided by the derivative of the power here with respect to x, which is minus in, plus the integration of this one is the same exponential function divided by the derivative of the power here. So it's minus in. Now I'm going to substitute by the upper bound and lower bound for each one of these. Okay, so I end up with this one. Okay, remember this one, e to the I n pi is cosine n pi plus I sine n pi. And this one is cosine minus n pi, okay, plus I sine minus I n pi. Sine n pi is 0 because sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine 4 pi is 0. So this term having cosine plus I sine, this one cosine minus I sine. So the I sine will be deleted with minus I sine. Even if it's not deleted, the sign is 0 at pi and 2 pi and 3 pi. So I have to remember, I have to change this one into cosine n pi plus I sine n pi, and this one cosine n pi minus n pi plus I sine minus n pi. Cosine minus n pi is the same as cosine n pi because cosine is even function. So I have all an I sine by n pi here. It will be deleted with minus sine I n pi. So I will have only this term. Okay. Remember, cosine n pi, cosine, if I put n equal to 1, cosine pi is 1. Cosine 2 pi is, cosine pi is minus 1. Cosine 2 pi is also my positive 1. Cosine 3 pi is minus 1. So I can write, instead of cosine n pi, I can write it as minus 1 to the power n. If n is odd, you have minus 1. Because cosine pi is minus 1, cosine 3 pi is minus 1, cosine 5 pi is minus 1. And when n is even, you have positive 1. Because cosine 2 pi is 1, cosine 4 pi is 1. So you have this formula for your Cn, which is better than finding An and Bn. Okay, now I have to distinguish, as I said here, between two types of n, the even n and the odd n. So it is better to go for letting n equal to 2k as even number. But if you would like to have the odd for the even number, I will have 1 here, right? So, and I have minus 1 here, so you end up with 0 for even number. But when you have odd number, if I represent the even number by 2k, n equal to k, so the odd number will be 2k minus 1. So when you have odd number, you have minus 1 to the odd power, which will be negative 1. So you will have -1 minus -1, you have -2. This is why you have -2. Okay? And the rest is I over by n, and you replace n by only the odd number 2k minus 1. So yes, this is very nice. I call it the sine wave. If you remember, this is a sine wave or the sine x, okay? -1 or +1. This is my function. Equal to, what is A naught? C naught is 0, so forget about it. So you will have only one formula here. You no need for C naught and A naught and AN and BN. You have only the formula of your Cn, which is this one, and you have to multiply by e to the I nx, which is the formula for Fourier series in the complex form. It is very simple, very easy. Main thing, you don't have to get 3 coefficients. You will find only one coefficient, which is Cn. Remember, you will have n odd number, not even number, but you can get back to the all the integers, positive or negative, by changing this 2k minus 1 into n, and n will be plus or minus 1. So I got this one because if I have even, n is even, I will have +1, and I will have here, I have here -1, so this one will be vanish, will be 0. This is why he let n equal to this one, and your n is odd number. This is the Fourier series in the complex form for my sine x function. Okay, how I can get this one? I believe I have a real function here, right? I don't have I here. I don't have any z here. I don't have any complex. So how I can get from this complex Fourier series, how I can get my real Fourier series for the same function? Instead of having A naught and AN and BN for this one to have the real Fourier series, it is easy to have the complex Fourier series and you change everything into real. So how I can change this one into the real one? So I can get the real Fourier series. Okay. So what he's doing here, I'm just take this one outside. This one I change it into n instead of 2k minus 1 over n, and I add this one. I split it into 2 y's instead of from minus infinity to 0 and from 1 minus 1 to minus infinity to minus 1, and from 1 to infinity. I have it only from 1 to infinity. How you do this one? As he said in the video, you have to add the conjugate of this one. And you, instead of having from minus infinity to infinity, you can go from 1 to infinity. What about the 0? I prove here C naught is 0. So I am not worried about n equal to 0 because I prove C naught is 0. Okay, so I change this sum from minus infinity to infinity into one sum from 1 to infinity. So I get the positive side. How I did this one? I split this sum into 2 sums from minus infinity to minus 1, which in this time n will be minus n. And I get the other half, the other positive half, 1 to infinity, which I needed. So I split this sum into 2 sums. The sum of this one in the negative one, so I have to change n by minus n. Okay, so I have a sum, but for 2 pieces, because this is a compound one. Okay, now how I can get this one? Get back to the I to the minus I nx, which is cosine minus nx plus I sine minus nx. So if you add this one, again, e to the I theta minus e to the minus I theta, it gives you sine. So yes, I can change my complex Fourier series into the real Fourier series only when I have a real function. But if you have a complex function, you keep it as a complex Fourier series. Okay, so yes, if you go and find A naught and AN and BN, you will have this one. Remember, this is odd function or even function. Can I listen to anybody of you? Or even or odd function, right? Because it is odd, I don't have AN or A naught. So yes, it is consistent with this one. Yes, A naught is 0 and AN is 0, which is linked to the cosine. So I don't have cosine in my Fourier series for this one because it is odd function. Clear? So now, even if you have real function, no need to go for the real Fourier series. You can manage with the complex Fourier series. And after you finish, right, you just split this sum into two sum. Sum in the negative side and the other sum to the positive side. What about the 0? I prove it, C naught is equal to 0. Because I know from the beginning this is odd function, this is why I will not have sign. I will have only the sign. So I split this one into two sum. And remember, this is cosine plus I sine, and this is cosine plus I sine. So if I subtract these two, okay, so I will have only sine. Let's go for the next example. Yes, he's asking you to find Fourier series of the function f of x equal to x squared. We know this is a parabola, right? So this parabola can in the range from -1 to 1. So what is my period here? Can I listen to any one of you? The period is what? What is the value of the function period? It is 2. Yes, it is 2. So half of my period, which is L, because my period is T, equal to 2L. So the half period is 1. So L is 1. Now I'll go for C naught. Yes, this time I have A naught. Why? Because I know from the beginning my function is even function, right? Because this parabola is symmetric with respect to y. And also, if I don't know the graph of the function, I can manage with the algebraic way. If I substitute x by minus x, I have minus x all square. So minus with the square will be deleted, so it will be positive. So I know from the beginning this is an even function. So I will never have any sign in my Fourier series. Whatever, it is a complex Fourier series or the real Fourier series. Now I find C naught, okay? Why this time I find C naught equal to a value? Because it is even function, so I will have C naught, which is exactly like A naught. Let's go for n is not 0, so I will go for the Cn formula, which is this one. 1 over your period, whatever your period is, okay? And integrating from minus half of your period to the other half of your period. Okay? Your function here, again, you are not going to multiply by cosine or sine, you multiply by the exponential function. When you go for the coefficient, you have e to the minus. When you go for Fourier series, you have e to the positive, right? So you will have this guy twice. Once inside the coefficient and once with the other sign, which is positive in the Fourier series and Fourier complex series. Okay. This is the integration by parts, right? Yes, in this case, you cannot use your calculator because your calculator is not working, normal calculator is not working with the complex function integration, even if it is line integral. This is the integration by parts. This is my u, this is my uv minus v du, okay? So you end up with all of this one, okay? So this is the integration by parts to find the Cn. Okay, again, remember sine n pi is equal to 0 and the cosine n pi is minus 1 to the. Why I'm saying minus 1 to the power n? Because if I have n odd, I will have minus 1. If n is even, I will have positive 1. This is why you have to get minus 1 to the power n. And n might be odd or even. So this is my coefficient, right? So why I forget about this one? As I said, when n is equal to 1, sine pi is 0. When n equal to 2, sine 2 pi is equal to 0. Also, this guy here will be also 0, whatever n is, odd or even. But this one will stay, but has two values. One is positive 1, and the other one is minus 1. The positive one when n is even, and the negative one when n is odd. So Cn, I can write it like this. So this guy is exactly this one, right? But the sign and here and the sign here is 0 because I know if n is 1, n is 2, n is 3, the sine pi, sine 3 pi, sine 2 pi, sine 4 pi, all of these one will be 0. So I will have only this one, which it has two value, minus 1 or positive 1. If n is odd, you will have minus 1 because cosine pi is minus 1, cosine 3 pi is minus 1, cosine 5 pi is minus 1. But if n is even, cosine 2 pi is positive 1, cosine 4 pi is positive 1, cosine 6 pi is positive 1, etc. So I can write my coefficient of my complex Fourier series like this one. What is a complex Fourier series? This is my complex Fourier series for my even function x squared. Okay, so this is the C naught plus, as I said, no need for the negative one, right? Okay, as I said, because I change this one into minus 1 to the n, and n, if it is even or odd, it will be included over here, right? And cosine, this is even function, so it will include only cosine, right? So I split this sum in the complex Fourier series into two sum, as I said, right? One for even function and one for the, for one for the even value and the other one for the odd value, as I said here. Okay. Now, yes, again, I will collect this one together. So I have e to the in by x, and I have e to the minus in by x. I know when I am adding e to the I theta plus e to the minus I theta, I will have cosine, which is fair enough because I said from the beginning, my function here, the one I'm dealing with, is an even function. So it is fair enough to have the cosine only in my Fourier series, whatever the real one I use or the complex one I use. But in the complex one, to change it into the real one, you have to be very careful because Cn has a counter from minus infinity to positive infinity, right? You cut this sum into two pieces, from minus infinity to minus 1, and the 0, 1, you have it separately, right? And you start from 1 to the positive infinity. Now, this is for you. I will ask you to do it by the real Fourier series and for a complex Fourier series. And you should have the same answer by the end. If you go for the real one, that's fine. If you go for the complex one, and when you finish, you have to split the sum for the Cn from minus infinity to positive infinity into two sums, from minus infinity to 1 and from 1 to infinity. And you find your C naught separately, right? First of all, before I leave you, let us discuss about this one. What do you expect the Fourier series will have for this function? First of all, your function is even or odd? Can I hear anybody?
Odd.
Yes. So you are expected if you go for the real series, Fourier series, are you going to go for A naught and AN?
No.
No, because it will be 0. Because this is odd function, so A naught will be 0, AN will be 0. So you will get only BN. You go for the Fourier series, you should have also only something linked to BN, which is a sign. So I will ask you, you have the presentation and the e-learning. Please do this one by complex Fourier series and by real Fourier series, and you should compare the two results to have the same answer. Okay? Please chat your name and your ID before you leave the meeting, and have a nice weekend.